Hi, and welcome to the first edition of Why Does It Do That? In this edition, we'll be looking at the classic situation, the person on a weighing scale in an elevator. As you just watched the video of the weighing scale, we must strive to ask, how does this happen? Well, first of all, as in the most important thing in physics, free body diagrams is what we need. So now we must create a free body diagram of the entire situation, and then create three separate ones to explain each one of them. The first one is for the person, then the weighing scale, and then the elevator. For the person, it's the force of gravity on the person by the earth, the force of normal on the person by the weighing scale, and now for the weighing scale, it's the force of normal on the weighing scale by the floor, the force of gravity on the weighing scale by the earth, and now finally for the elevator, the force of tension on the elevator by the rope, and now the force of gravity on the elevator by the earth. Watching the video of the elevator, you must have recognized, well, it didn't change constantly. It was going up and down at the same rate. Well, now it's important to recognize there are four situations that happen when an elevator is going up with the person on the weighing scale. The first situation is there's no acceleration of the elevator. Now this can occur because of two reasons. The velocity is a constant, or perhaps you're not moving at all, even if you're going up, or even if you're going down. In this case, the weighing scale will not change. The number that it shows will not change. Well, why does this happen, you say? Well, it's pretty simple. The weighing scale is the force of normal pushing up on the person. And if there's no forces affecting it in the y direction, then why would it change? This is the easiest situation of all four. And all you have to remember about this is, at a constant velocity, nothing's going to change. The second situation is when the elevator is going up, but it's also accelerating upwards. Well, obviously, when the elevator is going up, you're not going to sink into the floor, you and the weighing scale. That's not going to happen. So, because there's an extra force acting upwards, the scale therefore has to push upwards with an extra force on the person to accelerate the person's mass upwards. This results in a greater contact force between the two, the weighing scale and the person. Therefore, the force of normal between the weighing scale and the person has to be greater. And because the force of normal is what a weighing scale actually shows, well, it's going to be greater than the actual weight on it. To solve this algebraically, let's consider Newton's second law. Sigma F is equal to mass times acceleration that's acting on the person. The overall acceleration of the person is upwards, so mass times acceleration has to be positive. However, the only external forces acting on the person are the forces of gravity acting down, and also the normal force, F of n, that the scale applies upwards on the person, and also what the scale shows. So when you put those two equations together, you get sigma F equals mass times acceleration equals negative mass times gravity because that's the force acting down, plus force of normal. Now, as I previously stated, force of normal is what the weighing scale actually shows, so we're going to have to try to find that on its own. So when you set that, it becomes mass times gravity plus mass times acceleration. Well, as you can see, with all these extra values, the mass shown is obviously going to be greater than what it is. Now, let's look at the third situation. In the third situation, the elevator is going up, but it's also slowing down. In other words, the acceleration is negative. When does this happen? Well, it happens when you're going in an elevator at a constant velocity, but then slow down as you reach a higher floor. Now, the person doesn't float upwards because, once again, the elevator and the weighing scale and the person move as one. What does changes? Well, it's the contact force between the weighing scale and the person. The scale has to push less upon the person to support their weight. Therefore, the force of normal will be smaller. And because the force of normal is what is shown on the weighing scale, well, it's going to show a value less than the actual weight upon it. So let's solve this algebraically. Once again, we have to use Newton's second law. Sigma F is equal to mass times acceleration. Now we know acceleration is negative So the mass times acceleration side will be negative. And now we also know that the only external forces acting on the system will be the force of gravity going up and the force of normal. This scale applies on the person. So, looking at it, sigma f is equals to negative mass times acceleration, because acceleration is going to be negative, equals negative mass times gravity, because gravity always acts down, plus force of normal. Now we have to solve for force of normal, so it becomes force of normal equals mass times acceleration minus mass times gravity. And this value will obviously be less than the true weight of the person on the scale. Now we'll look at situation 4. Situation 4 is when the elevator is going down and it's also slowing down. In other words, the acceleration is positive. In this case, the elevator and the person are initially moving downwards at a constant speed and then slow down as they reach the floor of their destination. Now, what changes here? Well, the scale has to push upward a little extra force in order to accelerate the person's mass upwards. This results in a greater contact force between the weighing scale and the person. Therefore, the reading on the scale will be greater than what it truly is. To solve this using algebra, we have to once again look at Newton's second law. Now we know that the overall acceleration of the object, or the person, is positive. So mass times acceleration will be positive. And as in the other situations, the only forces acting upon the person and the weighing scale is the force of gravity and the force of normal. So it becomes like this. Sigma f is equal to mass times acceleration, which is positive because acceleration is positive, minus m times g, because as always, gravity is going downwards, plus f of n. And as always, we have to get f of n by itself equals mass times gravity plus mass times acceleration. And when you add these two together, it'll be greater than the actual value of the person on the weighing scale. Now on to situation 5. Situation 5 is when the elevator is going down and it's also speeding downwards. Otherwise, the acceleration is negative. In this case, the elevator is going down and it's speeding up to reach a lower floor. Now the person doesn't float upwards because once again the elevator and the person and the weighing scale move as one. So we know mass times acceleration is going to be negative because it's going downwards. The scale, therefore, has to push less force upon the person in order to support their weight. And because a lesser force is being pushed on by the scale, in other words, a lesser normal force, then the normal force shown on the weighing scale is going to be lower than the true weight upon it. To solve this algebraically, let's consider Newton's second law once again. Now we know that overall acceleration in this situation is negative, so mass times acceleration will be negative. However, as always, the only external forces acting on this is the force of gravity and the normal force. So let's look at it. Sigma f is equal to negative mass times acceleration, because as we stated, acceleration is going to be negative in this situation, equal to negative mass times gravity, because as always, gravity is always negative, plus the force of normal. So we have to get force of normal by itself, which is force of normal equals mass times gravity minus mass times acceleration. And when you solve for this value, it's going to be smaller than the actual weight resting on the weighing scale. So now on to the final situation, and probably the worst situation, free fall. Now this happens when the elevator cable is broken, and then the whole elevator, scale, person system would begin to accelerate downwards due to the force of gravity. Because of the magnitude of the acceleration downwards, because of the force of gravity, there would be no contact force between the weighing scale and the person. So technically, the mass on the weighing scale would be 0 because you're not really on the weighing scale. In other words, if you're in a free fall, I don't think you would really care about staying on a weighing scale. Well, that's the end of the explanation. Hope you learned, and I hope you enjoyed the video. So that was the first episode of Why Does It Do That?